Okay, welcome Physics 30s to your first lesson of the course. This is a bit of a review lesson, and we're talking about work and energy, things you've probably seen in lots of previous courses, but it's a topic that we'll build on throughout the course and look at some new applications, and you actually could get some questions in Chapter 1 that relate to these types of questions that we're going to be looking at today. So let's take a quick review of work and energy. Okay, so let's start with taking a look at the definitions. The definition of energy is the ability to do work, which I have never really found very useful because it just begs the question, well, what is work? If energy is the ability to do work, I need to know what work is. So we look up the definition of work, and it's a change in energy. But understand that I need to know what energy is, which I need to know what work is, which I need to know, it doesn't really ever seem that useful by themselves. These are true definitions, and it tells us that work is very similar to energy and they're related, but I never felt it gives a good sense of it. So let's look a little bit further at work and energy to see if we can connect them a bit better. Well, looking at energy, there's two types of energy. There's potential and kinetic energy. Potential energy is based off where an object is, its position, usually in a field, and kinetic energy is based off its motion, how fast it's going. So an example of potential energy would be gravitational potential energy. We calculate this mass times gravitational field strength times the height that you move in that field. So our position in a gravitational field will be potential energy. I sometimes discuss it because it could potentially fall and start moving. It could potentially turn into motion. We'll look later on in this course at electric potential as well. So looking at moving in an electric field, if I take a positive charge and move it closer towards a positive, well, it wants to repel from there. So holding that position that it wants to repel from would have some potential energy as well. We'll look at it more in depth later on. We can have potential energy in other fields too. Kinetic energy is a little bit more universal. If I have any mass from a bowling ball to a car to an electron and it's moving, I just go half its mass times velocity squared and I have its kinetic energy. So there's lots of types of energy. They fit either into kinetic or potential. So really energy is either motion or in a position that could create motion. So that gives us a little bit better of energy, definition of energy, which also gives us a better definition of work. If we're changing that, that means I'm either changing its position or I'm changing its motion. So to do work, I have to change how fast it's going or the position that it's in. Okay, so hopefully that gives you a better definition of energy and work, how they relate. There is an equation for work as well, and how I'm going to change its motion or its position is by applying a force over a distance. So that's a summary of these definitions and how work and energy are related. Let's take a look at an example of how you would apply this. So this one has a golf ball that is beginning at rest before being hit with a driver. The driver applies an average force of 14 kilonewtons. I had to look up how much force would be applied from a driver to a golf ball. It's remarkably high, a lot of force, 14,000 newtons. It's actually a reasonable answer from my research, but it only applies it for a very short distance before the ball leaves the club, 1.3 centimeters. And the ball leaves the club and in its flight, it reaches a maximum height of 20 meters above the ground. If there's no air resistance, what's the speed of the golf ball at this height? Okay, let's analyze this situation. There we got the golf ball on the ground, gets hit, flies this way, and we're looking for what its speed is at that maximum height. Its speed traveling this way, because it'll be going completely horizontal at its maximum height. Okay, so to start we have zero energy. At the end we do have some energy. We have potential and we have kinetic because it's up high in a high position and it's moving, so it's got kinetic as well. So this would be a situation where I had no energy, now I do have energy. Some work has been done on the system. How do we increase its energy? We applied a force over a distance. That driver applied a high amount of force, 14 kilonewtons, over a short distance, just a couple centimeters, to send it launching in this direction. Okay, so I'm going to move some things around here. First of all, write in that formula to get from there to here. Work was done to increase our energy. Okay, so now we're going to have that force times distance. The energy that we put in is going to equal potential and kinetic at the end. We're asking for the speed, so that's going to have to do with the kinetic energy. Let's fill in some formulas here. I can actually fill in the numbers for work. So I have 14,000 times 0.013. I have to have it in newtons and meters here to get my amount of joules for work. And I kind of flipped the order here, but in green, the kinetic energy, half mv squared, and in red, potential energy, the mgh. Let's simplify this a bit. So I calculate my work done. I did 182 joules. So I put that into the system. That's how much energy the driver gave the ball. And some of it's going to be kinetic and some of it potential here. I can plug in the numbers of half and the mass, but I'm still trying to figure out v squared. This number I can calculate entirely. So let's do that. Get 0.23 v squared, and a bit messy here, but 90.25 joules for potential. So let's just minus that 90.25 over, divide by the 0.23 square root, and we get a velocity of 20 meters per second when it's at that height. Actually, no, sorry, that's incorrect. I realized in the editing that I forgot to add another zero here, so it should be 0.046 kilograms, as we only have 46 grams for the golf ball, and 0.046 here. That's going to change our numbers a little bit here to 9.025 and 0.023, and that, when we put into correctly the equation here and get for our velocity, gives a much higher number of 87 meters per second for our final answer. That's remarkably fast, but without air resistance, the golf ball does travel pretty quickly. Air resistance slows it down a lot, so I think that is a more reasonable answer for this scenario. Okay, another application with energy to review is the first law of thermodynamics. And the first law of thermodynamics states that energy cannot be created or destroyed. You have a certain amount of energy, you can change it into another type, but it can't be created or destroyed. How do we apply this to questions is when we already have a system and we're not doing any force on it, how the energy is going to change in that system. So all we're going to write that the energy a system has off the start is going to be equal to how much energy it has at the end. It looks a bit more complicated when I write it like this, but it's just saying consider your kinetic and your potential at the start and your kinetic and your potential at the end, or which would be final. So these are just for initial right there and final at the end. Okay, let's take a look at an example of what this would apply to. We'll do some questions later on with electric fields that kind of relates to this question. So I think it's a good warm-up question for the course. Mass is launched from the floor to the ceiling at 10 meters per second. If the ceiling is 4 meters high, at what speed does the mass hit the ceiling? So just to animate that, say we shoot the mass up, it launches upwards, it's going to crash into the ceiling. How fast does it crash into the ceiling? Of course, it would fall down afterwards. We'll pause it in that position. So take a look at energy types. At the start, at the bottom here, it's got kinetic energy because it was launched at 10 meters per second. It's at the bottom, so we'll consider that to be no potential energy. At the top, it hits the ceiling, so it has some height. It's as high as the ceiling, 4 meters, but it also has some kinetic energy as well because it's moving when it crashes into the ceiling. So first law of thermodynamics says all my kinetic at the start has to equal my total energy at the top of the ceiling there. So my energy kinetic initial is the same as my two final energies. We're trying to solve for the speed at the end, so I'm looking for a value in EKF here. Let's plug in our formulas, and this looks like a lot of variables to deal with. And I notice they all have mass, but they never told me the amount of mass. They just said a mass. But fortunately, if mass is in every single term, terms are separated by equals, plus, or minus. So this is a term, this is a term, this is a term here. If mass is in every single one of those, or if any variable is in every one of those, we can factor it out, which basically means that we can cross out that term. It's going to make the rearrangement a little bit easier. So what I'm going to do, because I want to get this velocity, that's what I want to solve for, or VF, I guess I should circle the whole thing, is I'm first going to minus this GH to the other side. And then after I do that, so this is the minus the GH, to get rid of the half, I'm going to times by 2. And then to get rid of the square, we're going to square root. So plugging in all those numbers looks like this. We have 10 squared initially and 9.81 and 4 meters. See what we get there? We get an answer of 4.6 meters per second when it crashes into the ceiling. Okay, so to finish the video, we'll look at conservative and non-conservative forces. We saw from before that applying a force is going to change its energy. So let's look at when it's going to stay in the system, when it's going to leave. That's kind of a conservative and non-conservative force. So the definition here, a conservative force keeps energy in the system and it's considered recoverable. So I guess you kind of imagine if I have a pendulum hanging down and I pull it up to the side. To pull it up to the side, I have to apply a force over a distance to move it up to that side. So I've put in work. What happens when I let go? As soon as I let go, I get the energy back because it starts swinging and energy stays in the system. That would be considered a recoverable force and a conservative force. If I do work against gravity, gravity's a conservative force, I get my energy back. Even if I just lift a ball up and drop it, it pulls it back down, I get my energy right back. You might think, well, yeah, that seems kind of normal. What's the case where you don't get your energy back? Imagine that I was just pushing on a mass on a table. And I apply that same force, push on the mass on the table, and I let go, and nothing would happen. It wouldn't come flying back at me. It's just on a table. Where'd the energy go? It was in that sliding energy that was lost to heat, or that frictional force that took energy away from the system. So here it says a non-conservative force causes energy to leave the system as considered not recoverable, and friction or air resistance are these types of non-conservative forces. Okay, so what this does, it kind of adds the two things we've been talking about previously, work and then our conservation of energy. We have our same formula for energy at the start equals energy at the end, but now we throw in work. Okay, if it's a conservative force, if we're going to be increasing the energy there, we're going to have it plus. If it's non-conservative and it's leaving the system, it's going to be negative. Okay, so if it's negative here, it'd be like friction. We're going to take away energy. Positive, maybe I'm going to push on it, increase the energy of this system. Let's take a look at an example of that. Let's say we have a 2.5 kilogram object traveling at 1 meters per second. It's going to go down a 1.2 meter tall ramp with an angle of 40 degrees. At the bottom, the mass is traveling at 3.4 meters per second. How much work is done by friction, and what's the frictional force? Seems like a bit more complicated question. Let's take a look at it. Okay, so here's our mass. It's coming from the side, slide down, and at the end, it's supposed to be moving faster than when it started. 1 meters per second at the start, 3.4 at the end. First question, how much work was done by friction? Okay, so let's look at energy types just like we did in all the other ones. I start with kinetic energy, not a lot. We're moving slow, but we are moving with 1 meters per second for our speed. We also have potential energy at the start because it's up high on a 1.2 meter tall ramp. Okay, that's our energy off the start. At the end, all we have is kinetic energy because we're at the bottom of the ramp. Consider there no potential energy. And in that slide, I said not all the start is going to be equal to all the end because we're looking for the work done by friction. So friction is going to remove some energy to heat. It's going to do some work to change the energy of the system. Okay, so we're going to use that formula that we had from before. Work plus all our energy at the start equals all our energy at the end. And we're looking for this term. How much work was done? How much energy did we lose? So I'm going to move these over. I'm going to take the EKF and minus these two energies to the other side to get this formula here. Now that's a lot of EKs and EPs. Let's plug in our half mv squared for the EK and mgh for the potential energy. I should have colored these ones to make them line up, but hopefully you can see, yeah, those line up with those. Okay, I'm going to throw all the numbers in. It's going to look a little bit big, but here's all the numbers. I might be in the way of it a little bit. But plug all those numbers in. We have half 2.5 by 3.4 squared at the start. That's our initial kinetic energy. Our final kinetic energy there. Our initial kinetic energy here with 1 meters per second squared, and then our gravitational just above me over here. Okay, it's a lot, I know, but we can plug that in our calculator, and we should get a change in energy of negative 16.23. I was expecting a negative value for the work because energy was lost when it was sliding down the ramp. It was lost to heat due to friction. So the first part, how much work was done by friction? Negative 16.23 joules. Now we're not quite done there because it also added another question, what's the frictional force? This part's actually a fair amount quicker than the last one because this is a big formula, but we know that just work is equal to force times distance, what we saw on the first slide. Okay, so that's not too bad. If we're trying to solve for force, let's divide by our distance. So I'm going to take my work, negative 16.23. The distance in the question is 1.2 meters. But if you plug that in, you're actually going to get the wrong answer. Why are you going to get the wrong answer? Because it's a 1.2 meter tall ramp. That's this height. That's that number right there. That'd be the 1.2 meters. What distance does the friction act over is that distance right there. It's sliding along the ramp. So it's common for students to look and see a 1.2, throw that number in, but they didn't consider really the scenario or the diagram and what's actually happening. So I got to find the length of that, And if you're wondering, why were we told 40 degrees? I didn't want to do anything with that so far. This is where the 40 degrees comes in. Sometimes you're given information you don't have to use, but this is where the 40 degrees comes in. Unfortunately, if I know the 1.2 and I want to solve for the hypotenuse, I have my opposite trying to solve for the hypotenuse. We can use sine. Now, I didn't put the whole formula here, but it's sine theta is equal to opposite over hypotenuse. We'll rearrange for hypotenuse and get 1.2 divided by sine 40. My hypotenuse value of 1.869 as our actual value that we should be plugging in, the distance of the ramp. So let's divide that, having a number of 8.7, negative 8.7, because again, this is a negative force because it's taking away energy and slowing down the mass. And that's all we have for this video. So hopefully that helped you kind of recap some Physics 20 concepts as we get used to this new course. Hopefully that helped you out. Thank you so much for watching, and I will see you in the next video.